Hey everyone, it has really been some time before I post something. I remember last time when we last met, we were talking about independent events. Today we want to talk about something that is so useful in probability, and that is tree diagrams. Tree diagrams. Tree diagrams are so useful in tackling many probability problems. Let's write down something about it. So tree diagrams are a way of showing combinations of two or more events. Remember, we have discussed an event as a subset of a sample space. Okay, we shall see that each branch is labeled at the end with its outcome, and the probability is written alongside the line. We shall see that in a moment. Okay, so we have also talked about independent events, and we say that independent events, the probability of an event happening does not affect the probability of another event happening. So look at this situation. When we roll a die, we have discussed this in the most previous lesson, but when you roll a die, okay, and you score a 6 the first time, that's not going to affect the probability of scoring a 6 the next time. So when you have such a situation, those are independent probability situations, okay? So how do we use a tree diagram, okay, to visualize this kind of situation? Let's just see, okay, if a die is thrown twice, okay, what happens is, let's look at this. So how do we draw a tree diagram for a die which is thrown twice? Okay, so you can call this the first roll or the first throw. Okay, and when you throw a die and your aim is to get a 6, okay, you can get a 6 or you will not get a 6. Let me adjust this tree diagram so it can fit what I want to communicate. So we can get a 6 on the first row, or we may not get a 6. So the probability of getting a 6 is 1 out of the 6 faces. So this is a 6, and this is 5 out of 6. When you fail to get a 6, so not a 6. Now you try the second time, okay? If the first time you were successful and you got a 6, then you can still go ahead the second time, you roll, you can get a 6, okay? Or you can fail to get a 6. So this is 6, and this is not a 6, okay? Or it can be the other way around. The first time you did it, you did not get a 6, but the second time you do it, get a 6, and the probability here is 1 out of 6. So you get a 6, or it is 5 out of 6, and you don't get a 6, not a 6. So this is the first roll here, okay? I can try to highlight this if you want, and show you that this is for sure the first roll of a die. Oh, it is oh no, let me undo that. Okay, now the second time, this is the second time you are rolling, and, okay, so this is the roll 2, and here, how do you write the events? Okay, let me use this small box to write the events. So here it is 6 and 6. What about here? When we follow this branch, we move from here and then come along this line. It is a 6 the first time, and then not a 6 the second time. Okay, not a 6. Okay, so what about here? This is not a 6 and then a 6. Then here it is not a 6 and then not a 6. So that's how a tree diagram can be so useful. And how do we get the probabilities? To get the probabilities, you multiply the probability along the branches leading you to a particular combination. Like this combination is the first time you get a 6 and the second time you get a 6. So the probability is going to be 1 over 6 times 1 over 6. Okay, here it is 1 over 6 and even here it is 1 over 6. What about this other branch? If I move here and then come along here, okay, it is going to be 1 out of 6 times 5 out of 6. The first time you call it 6, but the second time you don't get it. Okay, here it will be 5 out of 6 times 1 out of 6. And this will be 5 over 6 times 5 out of 6. So if you throw a die, the probability that you don't get a 6 the first throw and the second throw is gonna be 25 out of 36. So this is how a tree diagram is really so useful in tackling many probability problems. Okay, let's look at some more examples. Look at this example. Okay, what is it? It says a bag only contains 4 blue counters and 3 red counters. A box only contains 5 blue counters and 2 red counters. One counter is taken at random from the bag and put into a box. A counter is then drawn from the box. Now the question is, what is the probability of getting a red counter from the box? Okay, this is a problem that we can easily solve using tree diagrams. But this is not an independent situation. This is a conditional kind of situation. So let's look at it. We have the bag, so solution. What we are doing, we are taking from the bag, okay, the bag, and then putting into the box. So what happens is, okay, from the bag, you can pick red, okay, this is red, or you can pick a blue, okay, and if you pick a red, the probability of picking a red from the bag, look, they are saying that a bag contains 4 blue and 3 red, so this is 3 out of 7. Or if you picked a blue, it will be 4 over 7. Now, if we picked red and we place it into the bag, into the box, so the second we shall have a box, okay? We have the probability of picking a red still, this is red, okay? And the first was red, okay? Or it is red, the first is red, and we pick a blue, okay? Or it can be this other situation, okay? We pick a blue and then pick a red. Or we pick a blue and then pick a blue. Okay, so we have to understand what we are dealing with. This is conditional probability because the probability of the first event affects the next one. Okay, let's see. So if we picked a red from the bag and placed into the box, we need to know what is the content of red in the box. A box only contains 5 blue counters and 2 red. So if you bring a red from the bag and put into the box, it will be 3. The sample space will increase by 1. Okay, 5 blue remains, but the red will be 3. So this is 3 out of 8. Okay, and this will be 5 over 8. Okay, if we picked a blue from the bag and placed into the box, okay, the red won't be affected, but the blue number increases to 6. So this becomes 2 out of 8, and this will be 6 over 8. Now, the question is, what's the probability of picking a red? Okay, now what I'm going to do, because I didn't write this so well, the way we would write a conditional situation, let me do this. Let me erase the first one. Okay, I want to write red here. I write blue here. Then here we are picking a red, and we are picking a blue. Okay, so if we pick a red, the first one is a red from the bag, and then the second, the counter we pick from the box is red. So we shall write here red. Okay, and the probability will be 3 out of 7 times 3 over 8. Or we can have a blue. Okay, you picked a red right from bag and then pressed into the box, but you are picking a blue. So this is 3 over 7 times 5 over 8. Okay. Or it could be the other way. You picked a blue from the bag and placed into the box, and now when you want to pick something from a box, you land on a red. Okay, this is going to be 4 over 7 times 2 over 8. Okay, and if we pick a blue, okay, what we picked from the bag was blue, and then this is 4 over 7 times 6 out of 8. Now, what are the events of interest? The events of interest are the ones leading us to red. Okay, we need this and also need this. Okay, so the probability of red will be this product plus it will be a product here. The product you get out of this, let me see, this is 9 out of 56, something like that. Okay, so 9 out of 56, 9 out of 56, and this is 8 out of 56. So the probability of red will be the sum of these two, 9 out of 6 out of 56 plus 8 out of 56. That is 17 out of 56. Let's write on this page. So we can start the probability of picking a red counter from the box is 9 out of 56 plus 8 out of 56, which is 17 over 56. And we are done. Okay, let's look at another example. Let me write it down. Look at this problem. A bag contains 4 red counters and 6 black counters. A counter is picked at random from the bag and not replaced. A second bag is then picked. A second counter is then picked. Okay, and now they are saying find the probability that the second counter is red given that the first counter is red. Both counters are red. The counters are of different colors. Okay, look at these problems and see how we can go about them. But the easiest way and the most straightforward way of tackling this problem is to use probability tree diagrams. Okay, let's look at this bag. Okay, it is having 4 red. Okay, there are 4 red and 6 black. That means that In total, we have 10 counters, of which 4 are red and 6 are black. So a counter is picked at random from the bag and not replaced. A second counter is then picked, okay, from the bag. So you pick the first and don't put it back. Then you pick a second from the bag. So this situation is no longer an independent situation because the first picking affects the second picking in terms of probabilities. Let's see this on a tree diagram. So to make our life simple, let's use R, okay, to stand for red counter. Is picked, okay. We use B, the other color is black, B to stand for black counter is picked. So in this bag, let's now develop the tree diagrams, okay? We are picking you can pick a red or you can pick, the first time we do it, okay, we can pick a red. This can be red or this can be a black, okay. That's the first time. So the probability of picking R, remember in this bag there are 4 red and 6, so this is 4 out of 10. And the probability of picking black is 6 out of 10. There is one thing you have to know about the probability tree diagrams. At every junction, the probabilities must sum to 1. So 4 over 10 plus 6 out of 10 is equal to 1. Now, if we picked red, let me use this subscript to mean red first and the black first. Or if you picked red first, okay, then you can pick red the second, P of red the second time, given that the first was a red, okay? Or it can be probability of picking black the second time, given the first was a red, okay? We are looking at this event, okay, or this possibility. We picked a red the first time and we are picking a red the second time. So it is a conditional because picking red the first time affects picking red the second time. We are not putting back. So if we pick red, okay, this is red and the red, okay. The first time is red and the second time is red. So this is going to be 3 out of 9. The sample space has reduced because the first red you picked was not put back. So we are now having the sample space reducing to 9 and the red reducing from 4 to 3. So 3 over 9. That's the probability of picking a red the second time, given the first was a red. What if we pick a black the second time, given we picked a red the first time, okay? Remember, in the first picking, it was a red, so the number of black was not affected. But since we did not put back that red we picked first in the box, in the bag, the sample space still reduced to 9. So this is going to be 6 out of 9, and this is red, okay? Then black. That's what we can write here. Okay. Now, what if it is this situation? Okay. You pick the first black, and then you are picking the second red. This is red the second time you pick, given the first was a black. Okay. What is the probability? This is gonna be, this is black and then red. So what's the probability of picking red? The 4, okay, out of 9, I think they are 9. Remember, you picked black, so the number of red was 4, so it remains 4. But the sample space reduced since you did not put the black back in the box. Okay, so what about this probability of picking a black the second time, given the first was a black. Okay, so here we have black and then black. Okay, so what do we get? This is the first is black, you did not put it back, so the second is black, that is a 5 out of 9. Okay, so let me put these combined events in boxes so you can get to understand what we're talking about. Okay, the events are always written at the end of the branch. So the probability that we pick a red the first time and then the second time we pick a red is going to be 3 over 9 times 4 over 10. Multiply the probabilities along a branch. Okay, these are the probabilities I'm multiplying along that branch. Okay, here it is going to be 6 over 9 times 4 over 10. And in this we shall have 4 over 9 times 6 over 10. Then this branch gives us 5 over 9 times 6 over 10. The most difficult thing when you are dealing with tree diagram is developing a tree diagram. The moment you are able to develop one, solving the problem is not going to be a problem. Okay, so let us see. The first question is, find the probability that the second counter is red given the first counter is red. Okay, so this is what they're talking about. The second was red given the first is red. Find the probability that the second counter is red given that the first counter is red. Okay, so what is the probability? P of red given red is simply 3 out of 9, which is 1 out of 3. Okay, then the question here says both counters are red. Okay, both counters are red. Let's see where we have two reds. Both counters are red. Is this okay? Is this so? This was this answered the first part. Okay, red given the first red. So both counters are red. How do we get that? Multiply 3 over 9 times 4 over 10, and the answer will be 12 out of 90. If you want, you can reduce it in the lowest terms. Okay, a third times 2 over 5 is gonna be 1 out of 15. Okay, 12 out of 15 rather. Okay, so that is it. Let's write the answers on next page. So the last one is the counters are of different colors is what we want to solve. Okay, counters are of different colors. Different colors. What's the probability? Let's look at the tree diagrams. Different colors, you have the probability of red 1 intersection red 2. No. Intersection black 2. Okay. Or it is the probability of black 1 intersection red 2. Okay. So if you are picking the first red, we said that was 4 over 10, and the second is black, that is 6 over 9. Okay, plus, okay, the first is black, that is 6 over 10 times 4 over 9, and this gives us 24 out of 90 plus 24 over 90, okay, which is 48 over 90. Okay, this is 48 over 90. You can reduce this in the lowest terms if you want. So, ladies and gentlemen, more problems are going to be solved in my next lesson. So, there are so many problems about tree diagrams I'm going to solve in the next lesson. So, we shall also talk about the Bayes theorem and how to use it basically in tree diagrams. And that will be the biggest part I want to discuss for any probability. So, let's do that tomorrow. Let's discuss more about this, and then after we shall start looking at the discrete random variables. Okay, don't forget to subscribe. Don't forget to recommend this for a friend. It is so important to share with your friends who are down there in lockdown. Okay, thank you so much for listening. Thank you so much for attending my lessons. I wish you the best.